Welcome to this video in which we'll talk to you about the for loops in OpenMP and the other features that we still have to go. So in the last video, we ended our discussion with a couple of examples about for loop parallelism, and in which actually we saw how with a simple directive, OpenMP would split the total number of iterations over multiple threads. And one way of assigning those iterations, for example, is to assign the first two, second two, third two, and fourth two to each one of the four threads that are available, and then to distribute one of the of each of the four remaining iterations over those threads when they finish the first bunch of threads. Of course, this is just one possible way this distribution would happen, and we will see how the scheduling of those iterations will happen and how the developer can actually control this scheduling. So more details about the scheduling of the loops and how the variables are considered inside the loop, the scope of the for loops, whether they are considered private or shared, and how to synchronize the access to the shared variables. So this will be the main concern for today, actually, the three main topics for today. Okay, let's start with the basic example. So we can use a OMP parallel for Pragma OMP parallel for directive, and then we write our for loop. If it consists of multiple lines, then we can add the braces for it. And as we have just said, in this case, those instructions that will be executed over each iteration inside the loops. For example, here we have n different iterations. So this number n would be distributed over the multiple threads that we have. So suppose we have m different threads, then in this case, each thread would take care of approximately, let's say, n over m different iterations, and would proceed with its execution. Okay, the execution of those this chunk of the iterations. Okay, so we talk about a chunk or number of iterations that would be assigned to each thread. So please note that if you don't add this for directive here to the pragma, then this would be considered a parallel section in your code that contains only one instruction, which is this for loop. And in this case, it means that you want each one of your threads to execute this. So if you write OMP parallel, simply, and then you write a for loop. Okay, so no matter what this for loop is doing, you are asking OMP to assign this task if it happens that it's a for loop. So you are asking OMP to assign this task or this line of code to all the threads that you have. So if the loop is making n iterations and then you have n different threads, so you'll end executing your code that exists here between the braces n times m times. Okay, so m times n times, because each thread will execute it already n times. Okay, so it's not at all the same as when you add this for directive and you actually ask to parallelize this for loop and to split and distribute its iterations among the multiple threads that are available for your program at runtime. Okay, so please pay attention to this detail. Another way to define for loops, typically you would have started already a certain parallel section in your code or region, and then you would have added multiple pieces of code here for initialization, let's say, by the multiple threads that you have. And then you reach a certain phase where you want to execute a certain for loop, but in parallel. You want to parallelize the whole for loop over the multiple threads. So in this case, um, as I told you, if you don't add this for directive to your pragma OMP region, then this for loop, as all the other lines, it would be executed m times, where m is the number of threads. But if you actually, sorry, if you add this for directive to your pragma directive, then in this case, this for loop would be distributed or split across the available threads. Okay, any piece of code that occurs after it or placed after it, it will be executed again by all the threads. Okay, so you see here we have a distribution across the available threads. Here we have the same code being executed systematically by all the threads. Let's consider a couple of work sharing examples related to for loops. So here we have a pragma OMP parallel for with two variables, a shared variable and a private variable I. So n will be globally seen by all the threads. Fortunately, it's accessed in read-only mode. So all the threads are just referring to this value n to check whether they reached that n or not. Okay, so it's not a big deal. However, I that is actually initialized and also incremented inside each iteration of the loop. Well, it has to be declared private so that each thread can work on a different value of I. So inside this code, we're just displaying the ID of the thread number, and the value of I, the value of the iteration. As an output, we see that, for example, the thread number 0 has worked on the threads 0, 1, 2, 3. Thread number 1 worked on the iterations 4, 5, 6, 7. Thread number 2 worked on the iterations 8 to 11, and thread number 4, 3 actually, with ID number 3, has worked on the iterations 12 to 15. So all in all, we have 16 different iterations, and each thread took one chunk, actually the exact number of iterations, which is 16 divided by the number of threads, which is 4, and hence each thread worked on 16 over 4 different iterations, so which is equal to 4. Okay, so all in all, they worked on so this is the total number of iterations, and this is the number of threads. So here we got the total number of iterations per thread. So this is cool, and if you run your code another time, you will see that same static assignment of the iterations over the thread has been done, but actually maybe the threads started and ended their work in a completely different way. And here is a third sample of how this code might run. So as you see here, the parallel for splits the for loop iterations into multiple threads. The shade and declares the variable and to be shared across all the threads, and the private I makes sure that a copy of I, a separate copy of I that is completely independent is made for each thread, so that when you increment I, actually the value of I that exists within a certain thread internally, okay? Let's say here, the value of I becomes 12. However, when the thread number 0 resumes working, it will find back the value that it had locally for I, which is 1. Okay, however, n is remain 16 all the time, all the way for all the threads, because it's shared and it's globally visible by all those threads. Okay, so let's consider this other example in which we have two different for loops. So a first one that is going from 0 to 7, and it's displaying the word A 8 times from 0 to 7 by displaying also the thread number, and then between brackets the number of the iteration. Also, we have another one that would do the same, but with the letter B. Just to show that we have two different for loops, let's call them the A for loop and the B for loop. As we shall see in the runtime, we have kind of an implicit barrier that has been done here at the end of the for loop. Okay, so because no iteration has been from the first for loop has been executed during the execution of any of the iterations or between any two different iterations from the second for loop, from the B for loop. Okay, so we see any barrier between them, although within each for loop, the order was not guaranteed, so the execution was really free, although we have a kind of a static assignment of the chunks. So the thread number 0 in both for loops have been assigned the iterations 0 and 1. The thread number 1 has been assigned the iterations 2 and the 3 systematically in both for loops, as if there is something that is happening by default. So first of all, we notice that we have a fixed chunk that is assigned and that is equal to total number of iteration divided by the number of threads. Okay, so this is the default chunk that is assigned to all the threads. And we also have a fixed distribution or assignment of those thread iterations or chunks, okay, of chunks to threads. So each thread in both for loops has been assigned the same exact chunk of iterations or work parcel, let's call it, okay, of iteration. So what if we have nested loops? So we have to pay attention because within nested loops, the second loop is executed systematically by entirely by all the threads. So only the first one is distributed among the various threads, but each thread would execute the whole for loop, the whole internal for loop. Okay, so the loops, the inner loops index must be set private. Okay, because otherwise you may have bad surprise in the output. Okay. So if we check what's happening here, we are displaying that A with the ID of the thread and with the values of I and j. So we can notice that each thread took a different value for I. Okay, so if we have 4 different iterations from 0 to 3, and we have 4 different threads from 0 to 3, so each thread number I worked on the iteration I number I. Okay, so we have a 3 and a 3 here. We have 1 and 1. Okay, so the thread ID was equal to the iteration number I. But each thread has fully worked on all the J's iterations, which are only 2. So A worked on the 0 and the 1 iterations. A1 worked on, or the thread number 1 worked on the 0 and the 1. The thread number 0, the thread number 2. So all of them, they worked on both iterations, J iterations. Okay. If you rerun the code once again and again and again, you'll see the same result. So maybe the order of the execution or the display of the messages between the threads would be different. We may also have this one coming between these two or after them. This doesn't really matter, but you will always see that the iteration j equal to 0 would take place before the iteration number 1, because this would be run sequentially. Okay, but you may have different iterations of I being executed in different order and in full parallelism. Okay, so it's good to review these examples. And so let's see how the scheduling would be done inside the for loops in OpenMP. So the first way of scheduling loops, loop iterations, is to divide them into pieces of size a chunk, and then statically assign them to the thread. So this is what you can define with the schedule parenthesis static um, um, uh, uh, directive or close, and then after the comma you can define the chunk. Okay, so by default the chunk, if the chunk is not specified, then the iterations are evenly, if possible, divided contiguously among the threads, as we have discussed earlier. Okay, so this is the default scheduling, and this is why we had the earlier results when we didn't specify any schedule, particular schedule. The other way of that you can schedule your for loops iterations is to assign to them a dynamic allocation. So in the static, for example, when we have, let's say, imagine this whole zone here defines the total number of iterations. So if you don't define a chunk, then as you see, if you have 4 threads here, they could work each of them on twice this chunk of iterations. Okay, so suppose this total is equal to 16, and here it seems that you have defined the chunk to be equal to 2. Okay, so in this case, forcing the chunk to be equal to 2 has assigned the first 2 iterations, the first chunks of 2 iterations to every thread, and then kept in mind that another chunk should be assigned to those threads. Okay, well, we don't know if these threads will take the same amount of time to finish those chunks, but it's too late. The assignment has been, and the distribution has been already done to those threads. So even if, for example, T1 finishes this chunk and that chunk at, let's say, moment number after 1 second, okay, um, um, and let's say the same happens for T2 and T3. So if all of them finish after 1 second, but T4, suppose that T4 is still struggling with this chunk up to the second number 2, well, unfortunately, we have to wait until it finishes after the second, and then it would also take 2 additional seconds to handle this chunk here. Okay, so and we will end up having 4 seconds of delay because T4 really ended late. Okay, so this is the disadvantage of the static assignment. It's really useful. It's faster to schedule. It's systematic for the runtime environment. It doesn't take any overload to think about what would happen and to check on at runtime which thread has finished or not. So the static assignment is really very easy to handle by the runtime environment, and it has no overhead for the management. But it's only useful when you know that all these chunks would take almost the same amount of work. So suppose that the work is harder after this half, okay? So also defining this chunk equal to 2 is helpful to make sure that each thread would work on 2 of the easy chunks, and then each of them, when as soon as it finishes its work, would jump to the next half of the array, let's say, to work on the other difficult chunks. Okay, so in case you have this insight about your data and about the complexity of your data and the time required to handle this data, and if it is somehow the same time distribution, then it's fine. You can stick to the static scheduling. However, if you are not sure which part of your code or your iterations or your data would take more time to handle or to process, then it's better to opt for a dynamic assignment. In this case, the loop iterations are divided into pieces of size chunk and dynamically scheduled among the threads. So this takes a certain overhead because the runtime environment has to watch all the time whether T2 has finished or not to reassign another chunk to it. So here it happens that it started assigning to T3 and T2 that were ready the first, then T1 and T4. It happens that T1, although it was the third to be assigned a chunk, it has finished very quickly. Maybe the data here is very easy to process, okay? Or maybe that core was not occupied by any other processes. So when T1 finished, as early as it finishes, the runtime environment of your C code of OpenMP has to detect this and to reassign T1 a new chunk, okay, dynamically. If the next one happens to be T4, then it will be assigned another chunk. If it's now T3, then why not? If T4 finishes that chunk very quickly, then it can be reassigned a new one, even if T2 is still struggling for a certain reason with this chunk of the iterations. Okay, and if no chunk is specified in the parameter of this clause, then by default the chunk size is assumed to be equal to 1. Okay, so the OpenMP will make a progress gradually, one iteration after the other. But this would make a large overhead on and for the actually context switching between the multiple threads. So it's highly recommended to increase this number when the total number of iteration is really big. So to guarantee that only few context switching between those threads will be made, okay? And if you increase the chunk size very largely, then you won't benefit anymore from the dynamic approach. This is why it's by default set to 1. So even if you have very short loops of size 10, you would benefit somehow from this dynamic allocation, okay? But if you have very large loop sizes, let's say thousands or millions of iterations, then clearly you should opt for a much larger chunk size. What about the last schedule mode? It's the guided schedule. Well, the iterations in the guided schedule are dynamically assigned to threads in blocks as the threads request them until no blocks remain to be assigned. So it's somehow similar to the dynamic scheduling, or except that the block size decreases each time. So this is why it's guided. So it decreases each time a parcel of work is given to a thread. So the initial block is proportional to the number of iterations divided by the number of threads. It's proportional to it. It's not equal to it. If it's equal to it, then it means we are having the static scheduling. It's not the case here. So with the guided scheduling, we have a certain compromise to be done. So suppose you have 16 different iterations, then maybe at the beginning you assign, let's say, 3 iterations to each thread, okay? This would sum up to 12, okay? So maybe we can consider another number, let's say we have 24, okay? So at the beginning, again, assign 3 different iterations to each thread, which is somehow 24 divided by 4, but also divided by 2, okay? And then we assign maybe 2 iterations for each thread. We will end up having so far 8 and 12 equal to 20 iterations, and then we have 1, 1, 1 at the end, okay? So so the number of chunks or the size of the blocks or the chunks that are assigned to each thread is decreasing each time. And beside that, it's dynamic at the same time, because we may not assign to T2 at the first iteration because T2 was not really ready. So assign twice for T4, let's say, and then later on when T2 becomes ready, we may assign to it and we may ignore T4 for a certain reason if T4 is still working on one of the chunks, okay? So we may, and the order actually, we are assigning to T3 and T1 those chunks. Later on, we may assign to T1 this chunk and to T3 that chunk. So T2 at the beginning here. So the order does not really matter. In this sense, it's really dynamic. What about subsequent blocks? So as soon as a certain thread finishes, it requests to be assigned a new block, and in this case, subsequent blocks are proportional to the number of remaining iterations, okay, divided by the number of threads. So each time we do a certain ratio to decrease gradually the number of iterations assigned to each thread. Well, this is really useful because very often the tasks to be done inside iterations are typically harder at the end. Okay, let's consider a typical example for instance, the calculation of prime numbers. Okay, so if you are creating multiple threads and each one of them is checking a different subset of numbers, very large numbers, to check whether they are prime or not. Well, it's clear that checking this for very large numbers or for larger numbers is harder than checking it for small numbers, okay? So clearly all the threads would struggle towards the end of the loop. And this is why, to guarantee that all of them finish at the same time, almost, it's better to decrease the chunks that are allocated to each one of them or assigned to each one of them, okay, to each one of these threads, okay? And to give them smaller chunks towards the end of the for loop so that they finish together towards the end, okay? The chunk parameter defines the minimum block size and the default chunk size is 1, okay? But clearly having a larger chunk size is good, and this is the minimum block size that would be allocated to the thread. So they might be allocated a larger or a multiple of this block size. Note that the compiler differ in how the guided close is implemented, as shown in guided A and B above, because with guided B, the chunks are already predefined and assigned to different threads, okay, and they are not of equal size at any moment. So from the beginning, the chunks that are associated to each thread are of different size and are gradually decreasing all the way, okay. But still we have this dynamic allocation. It means that we do not allocate the whole table, okay? So we allocate different chunks of the table or the array of the data that we have or the iterations that we have in hand to the various threads, and we allocate more of them to the first threads, less number of iterations to the subsequent threads, and then we wait until they start finishing their work, and then we reassign them dynamically the subsequent iterations, all the way while decreasing the number of iterations that is allocated to each thread. On this slide, we have a summary of these scheduling with defined chunks or without defined chunks. So as you notice here, we had all in all 32 different iterations from 0 to 31. Eight iterations have been assigned to each thread, regardless whether they're finally finished very early, a bit late, or very, very late. So we don't care which thread would finish first. We just fix the assignment, and we don't care if a thread finishes earlier and it becomes ready to handle one of these iterations. Okay, that's it, it's fixed, and we don't change our mind. What if we specify a certain chunk for the static? Well, in this case, it's kind of like a round robin or a modulus calculation that is done for the indices of the iterations. So the first thread, um, the first 4 iterations are assigned to each thread, or let's say each thread number I would be working on the iteration number I modulus the number of threads, modulus MB threads. So what does it mean? So suppose you are wondering which thread will be assigned the work or the iteration number 13. Okay, so you just do the modulus to 4, and you find out that it's equal to 12 plus 1 modulus 4, which is 12 modulus 4 is congruent to 0, and then you have 1 here. So this is why this iteration would be assigned to the thread number 1. Okay, so what's happening actually is that we are assigning the iteration 0, 1, 2, 3 to the first thread. Okay, so the first chunk, and then the next chunks, which are 4, 5, 6, 7, are assigned subsequently, then 8, 9, 10, 11, and so on and so forth. Okay, if the chunk was equal to 2, then we would have assigned 0 and 1 to thread number 0, 2 and 3 to thread number 1, 4 and 5 to 2, and 6 and 7 to 3. In this case, 8, 9 would go to 0, etc., etc. Okay, so it's a static. We don't change our mind regardless of what will happen, even if certain threads would finish before the others. We won't change our mind. It's not dynamic. With the dynamic allocation, by default, the chunk is equal to 1, as we said. And suppose the subsequently that the first assigned chunks are 0, 1, 2, 3 in this exact order to those threads 0, 1, 2, 3, then you will see that if thread, let's say, number 1 finishes the first, in this case, the chunk number 4, okay, the iteration number 4, it will be assigned to that thread because it really was the first to finish, okay? After that, thread number 2 finishes, so the next chunk, which is iteration number 5, will be associated to thread number 2, okay? 3 is the third to finish, then we associate with thread number iteration number 6, and then when 0 finishes, we assign to it the iteration number 7, and so on and so forth. So if later on, for example, we find that thread number 0 is doing well, so maybe it will capture very quickly the iteration number 12, okay, before the others. Well, if you specify a fixed chunk, the same process happens, but each time a new chunk of work is associated, well, this would be a couple of iterations because the chunk is equal to 2. The size of the chunk is equal to 2. It means 2 iterations. Okay. So what about the guided? So as you see in the guided, the size of the chunks is decreasing gradually, okay? And even if it's not necessary that all the threads finish at the same time. So here, after reaching this one here, so suppose you have an iteration number 32, well, this would be assigned to the third thread in this case, okay? Because it was the first to finish, okay? With the guided and a fixed chunk, well, we want actually, this would be the minimum chunk size. So this is why if we start with 4 and then we downgrade to 2 per thread, we do not allow ourselves to go to 1 per thread as here, because the minimum required chunk is 2. So we keep on associating 2 per thread. And once again, the idea behind these minimum chunk size is to prevent the overhead that is due to context switching between the threads. Okay, good. So another problem would raise actually with parallel for loops and parallel programming, and which is the problem of race conditions. I would just leave you with this slide at the end of this video to think about it, okay? And then we will discuss it during the next video, okay?